Hello everybody, I'm Davood Bakhshesh and the topic of my presentation is a degree 3 plane 5.19 spanner for points in convex position. First we have some definitions. A connected network is a graph GSE with vertex set S and S set E such that any 2 points PQ in S are connected by a path. And a geometric network is a weighted graph such that each edge of the graph is the straight line between its endpoints, and the weight of edge is the Claudian distance between its endpoints. Consider a geometric network. The dilation or stretch factor between a pair of vertices P and Q in the network is equal to the distance between P and Q in the network over the Claudian distance between P and Q. And the dilation or stretch factor of the network is equal to the maximum dilation between all pairs of points. What is a T-spanner? A T-spanner is a network with dilation at most T, or in the other words, for all pairs PQ in S, there is a path Q between P and Q of length at most T times the Claudian distance between P and Q. The path Q is called a T-path between P and Q. The length of a path is defined to be the sum of the lengths or weights of all edges on the path. There are many algorithms to construct a T-spanner with good properties for a given point set. One of these algorithms is the greedy spanner algorithm. This algorithm first sorts all pairs of points in non-decreasing order of their Claudian distances. Then it processes the sorted list in sorted order. For a pair UV, the algorithm adds the edge UV to the S set if there is no T-path between U and V in the graph computed so far. The generated graph is called path greedy spanner, and for short, greedy spanner. It is well known that the greedy spanner is a high-quality spanner in variant practice, and it has been proved that the number of edges and the maximum degree and the total weight of the greedy spanner are asymptotically optimal. What is a plane spanner of bounded degree? A plane spanner of bounded degree is a spanner whose edges do not cross each other and whose maximum degree is bounded by constant. This table shows some result of plane spanner of bounded degree. The table divided into two parts, points in general position and points in convex position. In 2017, Biniaz and others proved that for any set of points in convex position, there is a plane spanner of maximum degree 3 with stretch factor at mass 5.19. Here we present the Biniaz's algorithm to construct a plane spanner on a set of points in convex position. First, the algorithm adds the convex hull edges to the edge set. Then it finds the farthest pair of points. Next, it removes the farthest pair. Now we have two convex chains. The algorithm finds the closest pair of points between these two chains. Then it adds the closest pair to the edge set. Then the algorithm removes the closest pair. Now we have new convex chains. Then the algorithm recursively continues on the new convex chains. It has been proved that the generated graph is a plane 5.19 spanner whose maximum degree is 3. Here we propose an algorithm to construct a plane 5.19 spanner of degree at most 3 whose total weight is asymptotically equal to the weight of the minimum spanning tree. Here we also show that the total weight of the plane spanner proposed by Biniaz and others is unbounded. Okay, here we present our proposed algorithm. First, the algorithm adds the convex hull edges to the edge set. Then it finds the farthest pair of points and removes it from the point sets. Now we have two convex chains. Next, we apply the greedy spanner algorithm on the sorted list, including all pairs PQ of points, such that P belongs to the upper hull chain and Q belongs to the lower hull chain. Here there is a useful lemma due to Biniaz and others. We used it to prove the results. Let P and Q be 2 points in the plane. The lune of P and Q is defined the intersection of the circles with the radius, the Euclidean distance between P and Q centered at P and Q. Now let C be a convex chain with endpoints P and Q. If C is in the lune of P and Q, then the stretch factor of C is at most 2 pi over 3. Using this lemma, we prove that the generated graph is a plane 5.19-Spanner whose maximum degree is 3. We know that the running time of Dijkstra's single source shortest passes algorithm for weighted graph is O(n) log n plus m, where n is the number of vertices and m is the number of edges. Moreover, sorting the list of pairs of points in the algorithm takes O(n) squared log n time. Hence, a direct implementation of the proposed algorithm using Dijkstra's single source shortest passes algorithm has the running time O(n) cubic log n. In the paper, we showed that the proposed plane spanner can be computed in O(n) squared log n time. The main idea to reduce the running time is that we not to use the Dijkstra's single source shortest passes algorithm, and instead by a quadratic time pre-processing of the point set, we use an algorithm whose running time is O log n for each pair. Since there are O(n) squared pairs, the overall running time will be O(n) squared log n. Now here we will talk about the weight of the plane spanner proposed by Biniaz and others and the proposed plane spanner in the paper. First, we show that there is no upper bound on the total weight of the plane spanner proposed by Biniaz and others. Let P be a set of n points placed at the vertices of a regular n cone. Assume that n is sufficiently large. Clearly, the convex hull edges x of one edge is a minimum spanning tree of P. Consider this figure. This figure shows the plane spanner of P using Biniaz's algorithm. It is clear that the weight of the spanner is related to n. Hence, the weight of the spanner is unbounded. Now we present the main idea for that the weight of our proposed plane spanner is asymptotically equal to the weight of the minimum spanning tree. To prove the result, we use the leapfrog property, which is defined on a set of edges. It has been proved that any set of edges satisfying the leapfrog property has a small weight. That is at most a constant time the weight of a minimum spanning tree of endpoints. Now we obtain the following result on the set of all shortcut edges. Note that we call an edge between the upper hull and lower hull a shortcut edge. We prove that the set F of all shortcut edges in the proposed plane spanner satisfies the T and T squared leapfrog property with T is equal to 3 plus 4 pi over 3. Hence, the weight of the set F is asymptotically equal to the weight of the minimum spanning tree of the union of lower and upper, where the union of lower and upper is the set of all points of upper hull and lower hull. Also, we proved that the weight of the minimum spanning tree of union of lower and upper is at most 2 times the weight of the minimum spanning tree of S. To prove this, according to the monotonicity property of the traveling salesperson tour, denoted by TSP, we have the weight of the TSP of union of lower and upper is at most to the weight of TSP of S. And it is clear that the weight of minimum spanning tree of union of lower and upper is at most the weight of TSP of union of lower and upper. Then we have the weight of minimum spanning tree of union of lower and upper is at most to the weight of TSP of S. On the other hand, we know that the weight of TSP of S is always at most 2 times the weight of minimum spanning tree of S. Hence, the statement holds. Finally, since TSP of S only contains the convex hull edges and the weight of TSP of S is at most 2 times the weight of minimum spanning tree of S, then the total weight of proposed plane spanner is asymptotically equal to the weight of minimum spanning tree of S. Thank you.